Hello, this talk will be about green threads. If you didn't know about it, you're lucky because I'm going to explain a bit how this thing works. So, let's start. I'm Anas, I work for Comviews, I'm a backend developer there. I also happen to like open source very much and contribute sometime in my free time. I'm the maintainer of Django Redis, so if you also have questions about cache and Redis, come at our booth and I will be happy to talk about that with you. You can find me on GitHub at WisdomPil, and you can also send me an email on my work email. And yeah, you can also find me on LinkedIn in the Pycon page, or you can also search for me by surname, but my surname is a little bit complicated, so better to copy paste from Pycon website. So what are we going to talk about today? What are the things we're going to talk about today? Is our scalability, how it's defined, how we can improve it, how threads and processes compare, what are cooperative threads, a bit of benchmarks for a proof of concept, green threads in a Django app, and the Comviews experience into moving some service into green threads. I apologize because this talk might be too fast with a lot of content and a lot of slides, but I'm told they have only 25 minutes and they are very strict, so I need to go fast so you can have time to ask me questions. So yeah, the elephant in the room. Django does not scale well. But is it Django? Is it Python? Why people keep saying that Django does not scale well? To answer this, we need to take a step back and answer a couple of questions. First is how scalability is defined. Well, in my opinion, scalability is defined as requests per second within one instance of your web server. You can, of course, parallelize by adding more instances, but to have something that is very scalable, you need to be able to support a lot of requests within one instance of your web server. And how can we increase this? Well, the solution is easy. You need to parallelize somehow to increase this number. And here is the question now. How processes compare to threads in this case? Let's take the processes. We want more processes. What happens? That you will have X copies of your web server, and each copy will be consuming its own resources. So let's see an example. It actually works 100% of the time, although maybe it's not that efficient. Let's say that you have a web server that on average replies in 100 milliseconds, so you can support 10 requests per second, and every instance or worker, so from now on we can talk about workers, needs 100 megabytes of memory. But we want to support 10,000 requests per second. What happens is that how many workers do you need? Well, 10,000 divided by 10, you need 1,000 workers. And how much memory do you need? Well, 1,000 workers, 100 megabytes, 100 gigabytes of RAM. That's a bit too much. So yeah, let's look at threads. This way, you will not have too many copies of the same process because threads share the memory, right? And yeah, but so it also works, but not all the time. Because with IO-bound apps, it works, but it's not really efficient. So actually, both approaches work, but they are still not that efficient. And also with threads, you have another issue. You are constantly switching, and the threads are idle most of the time, right? So, and also in the processes, it's the same thing. What happens is that you over-provision for your peak time, right? To be able to support more requests, you need to be able to have the peak the peak resources ready. And with threads, as I said, you have the problem of scheduling. Scheduling becomes a problem due to the nature of Python. Actually, in Python, you can run only one thread at a time. I'm pretty sure someone here already heard about global interpreter lock and how threads are implemented in C Python, right? So that's also not very nice. And then, yeah, the interpreter does not know which thread needs to be scheduled at a specific time. So let's talk about execution time, for example. You have a thread that loses execution time right when it needs it. For example, you're calling an API, and you get a response, and you need to do things with that response. But your thread loses execution time because the interpreter said, no, I want to give time to this other thread. And this other thread is sleeping because it's waiting for the response from a database query or an external API. So you see, like, useless context switch, you waste time, someone gets CPU cycles and it cannot do anything. Or it really wants to do something, but it doesn't have CPU cycles to do that. Execution time, CPU cycles, same thing. What if we could solve all of these problems, right? That's the reason of this talk. So I have the solution for you. Don't worry. We can do that by controlling when a thread is executed. We can be more efficient into giving time or CPU cycles to our threads. And here come the green threads. Green threads, also known as greenlets, cooperative threads, are actually lightweight threads. They are, the main two things is that they are cooperative and sequential. What does that mean? Cooperative because they can cooperate between themselves and say, I need time, you don't, and so I need to wait for something to finish, DB query or external API call. So I don't call me again until I have my data. And sequential because they run one at a time. This is quite important because of how they are implemented. Let's look at how they are implemented. They run in a single thread. They use an event loop. The event loop is the scheduler. The event loop is the one that decides who gets execution time. They're also easier to implement. This is the sequential part, because since they run one at a time, you don't really need to put locks, unless, of course, you can still write bad code and need locks and semaphores between threads, but let's say you're a smart person and you don't have that issue. What is nice, it's actually that this is for every event-driven app. It can be that your app, you have a graphical user interface and you're waiting for a key press event, and you need to execute some code when a key is pressed, or you are dealing with streams, messages, your message broker just has a new message for you, and you need to execute some code when this happens. Or you are writing a video game, and the entity just needs to be visualized and rendered by the engine, because the player is looking exactly at that place, right? This is also a bit of, you can see the same in callbacks. So your callback is being called when something happens, like if you're writing an Android app or whatever. But yeah, how to be cooperative in a web server? That's quite easy. Web servers usually either call other APIs or spend time calling the database. So you can just say, when you call the database and you need to wait for the response, you can let other green threads do their job. Maybe they need to manipulate the result of a query that just came back, right? Let's look at click twice. Let's look at an example. You have two requests arriving at the same time, one worker. You receive the request, point number one. You call an external API or the database, does not matter. Point number two. Point number three, you get the data that you need. And number four, you return the response after, I don't know, you change the structure or whatever of this JSON. Doesn't matter. So you see here, we cannot do two things at once. So second request needs to wait for the first to finish. In a cooperative version, it's a bit different because when you actually call an external API, the second request can start doing its thing. So call the view, do whatever checks you want on the JWT token and so on, and then call as well an external API. And when second request calls the external API, the first request might get the result of the request it made. So now the first request can finish while after it finishes, it says, okay, I'm finished, the event loop, I'm done. And the event loop says, oh, there is actually request B, and I can give it control and do its thing. And now if we go back, you see that actually the time is a bit different for the second request. This means that you are going to increase the request per second by quite a bit. And this is why people love async and await so much, and this is why people love fast API, IOHTTP, or even Node.js. As a matter of fact, they're all built on the same library, which is libuv. I strongly suggest you to look at the design implementation of it. It's quite nice. It was built for Node.js, but then they opened their API, and it's leveraged by a lot of other libraries. I will show you some examples, and in the demo app, there are some links, and you can read more if you really like. But yeah, putting await async everywhere is not an option. Let's say you have a big Django web server, and you need to rewrite in fast API. Oh yeah, everyone is excited, but you need a few months to do that, and your company will not be happy to pay you to rewrite your entire code base. Let alone find all the libraries that you need implemented in an async manner. So with the definitions of method that starts with the async def, right? And how can this be done for a standard WSGI app like Django served by Unicorn? Well, I have a solution again for you. This is GiveEnt, for example, which also uses libuv under the hood. GiveEnt is a Python library based on Greenlets that implement green threads in Python. There are many others. There is like Stackless, for example, that's also quite nice. It's some kind of async IO. So it's the same. It's just much older, and it doesn't start with async. And apps can be written with the GiveEnt natively, which is basically like having a Python standard library. So you have threads, you have locks, you have everything. It's like a async.io library. In async.io, you also have lock and queues and so on, and you can actually await queue.get. And in GiveEnt, you don't have to give the await. It's just queue.get, and you will get the result asynchronously. But there is a catch, because GiveEnt provides a different tactic, right? This is the nice part about this talk. This tactic is called monkey patching. So what GiveEnt does is basically it replaces standard code with the GiveEnt code. Similar to when you are writing tests and you're mocking some class to change the behavior, it's kind of the same. It's just that your code is saying import queue from queue, and GiveEnt will say, oh, I know queue, I can change it. I can make it green thread capable. Which means that you don't need to write await or yield anywhere. So no code changes. It's like someone just took your code and put async await everywhere, and you just didn't notice. So yeah, how about Unicorn? In Unicorn, you can enable it by changing the worker type. So you have your nice Unicorn configuration with the whiskey. It's the same. You just find the implementations that are green thread capable. But of course, there are bad things can happen. There is a catch. Libraries need to be able to be patched natively by the event. So so if the library is written completely in Python, that's quite easy. If not, then they need to have their GE event implementation that does the monkey patching. Where GE event cannot. Otherwise, it's like using a sync function within a sync, and you're taking the event loop the whole time, and you're not cooperating with any other thread, actually. Usually, this is a problem with libraries that have C extensions. So, if you, for example, Postgres, we will take a look at that later. Now, I want to show you the demo app to prove a concept. This app has two APIs. One is CPU bound, one is IO bound. It has two Unicorn configs, one with the event workers and the other with sync workers. And it has the same code, so no code changes. And it's written in Django because we like Django, and I hope you do too. So what the CPU bound API does, it makes a sum of numbers between 0 and a random number between 100K, and 10 million, just to waste CPU cycles and show you how to not use the event loop. And there is an IO bound API, which calls an external serverless API that sleeps between 100 milliseconds and 1 second, and then it returns a response. This is just to simulate an external API that is slow. Yeah, these are the Django views. It's quite easy. You can see that there are two functions that are not here. I will show them in the next slide. So CPU bound calls slow sum, and IO bound calls random sleeper. And these are the functions. Slow sum is quite easy. Call random sleeper is also easy. And it uses requests, which is a very common library to make external API calls. Serverless API, also known as random sleeper. It has this handler, so it's also quite easy. You just sleep and return how much you slept. We made some benchmarks using Locust, which is actually built on top of the event to make things more concurrent. So you see, like, circle is closing, a bit of things start to make sense. This is the Locust file. You just sleep between 1 and 2 seconds and call an API that can be CPU bound or IO bound. Let's look at the IO bound results. We have a sync version of Unicorn, which has 20 workers, and the event version has 2 workers with 1,000 concurrent connections allowed. We are not going to go that far, but you will see the difference much earlier. But it's very important, 10 times less memory. And these are the results. Average response time. Sync is the red, I think. Our designer would not like that, but yeah. And you see, like, 1.9 seconds. And the event, 2 workers with users change between 80, 200, and 250. Response time is always the same. And look at requests per second. You see the difference. Like, it's quite nice. It's quite nice. The event can handle 4 times more throughput with 10 times less memory footprint. Okay, let's look at CPU bound. In this case, we changed a bit the configuration because we wanted to give the same number of workers just to show that the result will not change much. 1,000 concurrent request connections does not make a difference because you're taking the event loop the whole time anyway. What are the results? Well, actually the same. Yeah, requests per second is a bit higher, but you see 21 and 22, so like 5% is not really relevant. It's not like 4 times and 10 times less, 4 times more requests per second and 10 times less memory. So yeah, most web apps are actually I/O bound and can benefit greatly from this change, but not all of them. So it depends on case-by-case basis. And some libraries can be patched, so you might have to do your magic uh, if you really want to take on this. What's the conviews experience? We moved to Gevent for one of our main services that was the bottleneck when we do our usual load testing, just to check if everything is still alright with the main flow. We chose this service because we saw that on average it would take 50 to 60% of the time calling other APIs or the database. It wasn't slow at all, we just wanted to increase requests per second because I really didn't want to see that much numbers of servers. And the result was, well, that service stopped becoming the bottleneck. So good, you find other things to fix after, and that's nice. So how to do that for your app? Well, first and foremost, you need to know your dependencies, what you're really going to do, right? You cannot like, oh, let's switch and see if requests per second go up. Well, you could. I do not advise to do these things blindly. Most of the packages work out of the box, so you are safe. PyMySQL, Elasticsearch, Mongo, Redis, Cassandra, Request, a lot. If your app just opens a socket and waits for the response, that's patched. If your app uses threads, Gevent patches threads to use green threads. If you're using standard library, no worries. In the case of Postgres, it's a bit different because you have C extensions and libraries like libpq. And yeah, PsychoGreen is a package that was made for that, so that it can do all the monkey patching so that you can use your library, you can use PsychoPG with Gevent or EventLab, which is another green thread implementation. Then you might have to do the connection pooling by yourself if it's not implemented. We had to do that in our service because of how Django does connection pooling. It's not Gevent friendly, and if you don't change the engine, you will just see your connections going up, and not being reused. So there is a package for that. You will see that in the repository of the demo. And that's pretty much it. Special thanks to two of my colleagues, Justus Ambrizas, which is a designer, and he made all the visuals. Sorry, Justus, this is red, and this is not the right copy. It should be like this. And thanks to another Justus the developer. And yeah, he helped me writing the code. There is not much code, we just wanted to do this together. And yeah.
So we have still a few minutes left. So
yeah.
If you have any questions,
please
just take them now.
You find the repo here, and you can come and chat with me in our book.
I have a question. When you say it doesn't work with certain libraries, does it work in the sense that it doesn't speed them up, or does it break?
No, it doesn't speed them up.
Okay.
If you take, even if you have async, if you're using async IO and you have a library that takes the event loop the whole time, then why use async IO? Like even, oh, let's use fast API, but then I have a library that takes the CPU the whole time and the event loop the whole time. You're not going to benefit from it.
So have you saved some cost at your company by like implementing the?
Yeah. I cannot give you the numbers because we made a lot of changes and our configuration is quite complex. We had also some memory leaks and so on with some libraries, so it's not relevant, but we were able to actually support like 2 or 3 times more load without breaking a sweat and without changing the response time, which is important. Yes?
So are you basically saying there is no disadvantages?
It depends on your app. If your app is CPU bound, then by changing you will not change anything. You saw like CPU bound and IO bound APIs, and there was no change. So I believe that, and also the connection pooling. So if you don't do the connection pooling and so on, then you're just going to waste time and not get any benefit. So
But that's the worst part. So either there is no changes at all, either there's speed up like in place.
okay, there is no change at all, but you have to change. Maybe you have to do the connection pooling. If you don't do the connection pooling, you're going to waste 20 milliseconds every time you need a connection. So you might have issues, and it might not be worth it for you. Any more questions? I don't know
And if worker has any issues, so impact the threats will be bigger, I guess.
what, sorry?
If worker has some issues, for example, I don't know, crashed.
Well, that's always an issue.
Yeah, but if you have many threads used at the moment, so impact will be bigger than using that.
Yes, of course. I don't know how can.
Disadvantage.
Yeah, I don't know actually how you can break it, but yeah, that can
It's
be
possible.
possible. Yeah, everything is possible.
Thanks, Hannes.
Is
And,
having issues, so statistically speaking, there, if you use more workers to do the same thing, you will have more workers having the issues, so therefore this is not.
So if you have any questions, you can talk to Hannes outside the conference room. And since our time is now over, thank you for being here, and thanks, Hannes, for